Flux density homework, problem 3, part 2. So we end up with an expression for q that involves another integral. However, that integral, there is also one identity that we can use, which is this one right here. We're going to select that a equals to minus 1000, and we just replace the value of that identity. So at the end, we will have q equals to 8 times 10 at minus 9 pi radius square e at minus 1000 radius over minus 1000 minus, because, well, minus and minus because plus 2 over 1000 times the result for that. That means e at minus 1000 radius over 1000 square times minus 1000 or minus 1. All that evaluated 0 to 0.001. If we evaluate this charge, that means we replace these R values with 0 and 0.001. We end up with something like 4 times 10 at minus 9 pi. Oops, not pi, only like that. Nanocoulombs. And that would be the answer for part A. For part B, we're asked to use the Gauss law to determine what's going to be the value for the flux density at a radius of 1 millimeter. So let's calculate it. We will not use this. We will only going to use the result of the charge. If we recall, Gauss law states that flux equals to closed surface integration, flux density, differential surface equals to Q. We already know what's the value of Q. So we need to get what's the value of the differential surface. That for a sphere, it's gonna be radius square sine of theta d phi, and radius becomes a fixed value. So we'll get the double integration of d times ds, radius square sine of theta d d phi. This is going to be for theta phi from 0 to pi, from 0 to 2 pi. And radius is actually a fixed value. D, we consider it as a fixed value too, that can go out of the equation, and we can rewrite this as d radius square integration from 0 to pi, 0 to pi of sine of theta d phi. Now, once again, we face the same integration. If we integrate d phi from 0 to pi, we're going to get phi evaluated from 0 to pi. If we integrate sine of theta d theta from 0 to pi, we're going to get minus cosine of theta evaluated from 0 to pi. All that words to say, we will get dr squared minus cosine of theta evaluated from 0 to pi times phi evaluated from 0 on 2 pi. This becomes 2, this becomes 2 pi, and we'll get the expression d r squared 4 pi. And we know that's going to be equal to the charge. So what we need to do is to replace the charge in here and solve for the value of d. In order to do that, make this board. Uh, and the expression at the end will be d equals to q over radius squared 4 pi, always in the radial direction, and we will get 4 times 10 at minus 9 over radius squared, but radius 0.001 squared, 4 pi AR direction. If we solve of the numerical values in here, we will get that the flux density at the radius equals to 1 millimeter would be 3.2 times 10 at minus 4 nanocoulombs. Sorry, minus 9 nanocoulombs per square meters. Just like that. That's the answer for part B.